All right, last class we left off. We were learning about converting things. We learned about how to make conversion factors. We take two things that are equal to each other. For example, 2.54 centimeters and 1 inch. Those two things are equal to each other. If we divide both sides by one of them, doesn't matter which one we divide by, then we get both of the units on one side and the other side turns into a 1. The magic of conversion factors. If we multiply by this 1 inch over 2.54 centimeters, and we have units of centimeters, we've got a centimeters then on the top that we would have been starting with, centimeters on the bottom in our conversion factor, poof, they disappear, they turn into a 1, they go away. And now we would have new units of inches. If we wanted to go the other direction, we would just flip the top and bottom of our conversion factor, no big deal. So a lot of our unit conversion problems will take kind of this form. We'll have some information that we're given. I usually underline that in green. We'll have some information that we're trying to get to. I'll usually underline that information or write that information in this fuchsia or pink. And we'll have some conversion factors, one or more, in the middle. And again, whatever our starting unit is, that's the unit that we want on the bottom in our conversion factor. We can rearrange stuff in math, so we could actually write this given unit, we could shift it over to be under our given units over here on the left. It would be the same thing mathematically. And so those given units would then cancel out and the units that we want would show up. For example, how many centimeters are in 12 inches? So inches has the number, that's our given. So we're going from 12 inches, not to feet, but to centimeters. And so we're going to multiply by a conversion factor. There are 2.54 centimeters in 1 inch. We had these conversion factors up on the previous slide. And so when we do this, the inches, the units of inches, we've got 1 on the top, 1 on the bottom. Those cancel out. We can also ignore the 1 that's on the bottom here because dividing by 1 doesn't change anything. And so what we would put into our calculators is 12 times 2.54, and the units that come out are the only units that are left, which in this case is centimeters. So let's figure out what that number is. 12 times 2.54 gives us 30.48 centimeters. 12 has two significant figures, so we would round this to 30 centimeters, and we would need a little dot after our 0, or we could rewrite it as 3.0 times 10 centimeters. Either of those is fine for sig figs. Questions? Great. So general problem solving strategies. Typically, we want to figure out what we are given or what our starting point is. We want to write those numbers down with their units. And things that have per, so like miles per hour, mph, miles over hours, that's what that is. Miles per hour, per just means divided by. Those might be used as conversion factors. Typically, my go-to for our starting point is something that has just 1 unit. Some things secretly have 2 units. We'll talk about those when we get to them. We want to start with something that's just got 1 unit. It doesn't really matter. We can start with a conversion factor. I just like starting with something that's 1 unit. So we'll identify a bunch of stuff that we're given. We might be given conversion factors. And then we also want to identify the endpoint, the find. This is usually next to a question word. If it's a question. Sometimes it's not a question, it just tells us what to do, but oftentimes these will be next to question words. That'll come in handy because some of the word problems that we do kind of feel like they're written backwards. And so identifying where the question word is and then just looking right after that, that'll help us identify what we're actually looking for instead of having to like do all the mental gymnastics of trying to figure out what the question's asking. And then we'll want to come up with a solution map to get from our start to our endpoint. And we might need multiple steps. So usually for the way that I'll solve problems, we'll write conversion factors under each of the arrows on the solution map, or just two things that are equal, and then we'll turn them into conversion factors later. And then we'll write the whole thing out and solve it. And then we can use a calculator once we get to the end. And then at the end, we want to check. We want to think about, does our answer make sense? Do we have the correct units? For a lot of the problems, we won't necessarily have a good, like, automatic gut feeling sense about, like, does the size of this unit make sense, or does the size of this number make sense given the inputs? I'll talk about how I identify some of those if they come up. We also definitely want to make sure the units are correct. One of the advantages of this method of writing everything out before we plug stuff into our calculator is we can clearly see what we're doing. We can also cross out our units as we go and make sure that the only units that we have at the end are the units that we want. Sometimes if you put a conversion factor in upside down, you end up with nonsense units. All right, we want to convert 288 centimeters to yards. So 288 centimeters is what we're given. We're going to yards. So solution map from centimeters to yards. We know that we can go from centimeters to inches. We might know how to go from inches to yards directly, but let's just say that we're going to go to feet first, because that's kind of the middle unit. And from feet, we can go to yards. Then we have to either rack our brains, check our yellow sheet, or look up conversion factors for these. So 2.54 centimeters equals 1 inch. That's what we're going to be using for our first step. For inches to feet, there's 12 inches in 1 foot. 12 inches equals 1 foot. And from feet to yards, our last step, 3 feet equals 1 yard. And once you've got some practice with these, you might find yourself just skipping past these two things are equal and putting it directly into conversion factor form with a number over another number. So for example, we're starting with centimeters. So in our conversion factor, we're going to need the centimeters part to be on the bottom to cancel out centimeters. So we would be using 1 inch over 2.54 centimeters. And then for our second step, inches to feet, starting with inches means we want inches on the bottom, feet on the top. So 1 foot over 12 inches. And for the last one, same idea. We're trying to get to yards, 1 yard over 3 feet. So you might just write them down in the conversion factor form just from the get, so that it's less stuff to write, maybe. And then putting it all together for the calculation, we bring our units out, or our number out. So 288 centimeters. We got a couple of conversion factors that we're going to do. We're just going to follow our solution map. So starting from centimeters, our first arrow is our first conversion factor, 1 inch over 2.54 centimeters. Our next step, I separate everything we're multiplying by these vertical lines, and then this long line through the middle, just to keep our numerator, our top part, and our denominator, the bottom part, separate. So our second conversion factor, 1 foot over 12 inches. And we can cross out some units. So we've got centimeters, centimeters, we've got inches on top, inches on the bottom. So we can cross some of those out. Should have done that from the start. And then our last conversion factor, 1 yard over 3 feet, which works out perfectly because now we've got feet on the bottom, feet on the top, feet everywhere, cancel them out. And the units that are left are yards. So carry the yards through. Based on the way that we've written out the conversion factors, assuming we didn't get the numbers mixed up, assuming the 2.54 goes with the centimeters, we didn't accidentally flip it. This tells us if we plug this into our calculator correctly, we will get the right answer. We've set up the solution map appropriately. So 288 divide by 2.54, also divide by 12, also divide by 3. And the number that we get out is 3.1, round our 4 up to 5 because the next number is a 9. 3.15 yards for 3 significant figures. 2 ways that I imagine you might put this in your calculator. 288 divide by open parentheses 2.54 times 12 times 3 optional close parentheses. Or you could also do 288 divided by 2.54 divide by 12 divide by 3. Those will both get you the correct answer. Questions? Cool. All right, one for you to try. Convert 9,255 cubic centimeters to gallons. 1 gallon is 3.785 liters. All right, an important piece of information that you'll need to solve this problem. Cubic centimeters are the same as, or equivalent to at least, milliliters. So 1 cc equals 1 cubic centimeter equals 1 milliliter, which gives us a conversion factor from cubic centimeters to milliliters. So starting with cubic centimeters, going to gallons. From cubic centimeters, we can go to milliliters. 1 milliliter per 1 cubic centimeter. From milliliters, we can go to liters, because that's a metric prefix conversion. There's 1 liter in 1,000 milliliters. And from liters, we can get to our desired unit of gallons. 1 gallon is equal to 3.785 liters. Any questions about the solution mapping? All right, so 9,255 cm to the 3. 1 mil over 1 cubic centimeter. Units of cubic centimeters cancel. 1 liter over 1,000 milliliters. The milliliters cancel. In our last conversion, 1 gallon over 3.785 liters. The liters cancel. And we're left with units of gallons.
For our gallons on our sheet, it's 1 liter or 0.26417 gallons.
Yeah, so if you're looking at the yellow sheet, there is one that says 1 gallon or 1 liter equals some fraction of gallons. There's also 1 gallon, and then there's the same number of liters. You can use either of those. It doesn't really matter. It should be the same. All right. So for plugging this into our calculator, we're going to do 9,255. We've got a bunch of ones on the top. We can ignore those. We've got a 1 on the bottom. We can ignore that. So we're going to divide by 1,000 and then also divide by 3.785. So 9,255 divide by 1,000 divide by 3.785. And this gives us 2.445 gallons after we round for 4 significant figures. If you think of liters as being the same size as quarts, which they sort of are, we would have 9.255 liters, which is about 9 quarts. 4 quarts in a gallon. We've got a little more than 2 gallons. That kind of matches up with what we get out as our answer. We can also do conversions using metric prefixes. We'll be using metric prefix conversions a decent amount. So we can make conversions between a base unit, any base unit, like meters, seconds, kilograms is our base unit, but I'll put grams. So we can convert between base units, units without a prefix, and units with a prefix. So for example, for 1 kilometer, the kilo prefix means 10 to the third power. And so we can substitute in, for the k, we can substitute the 10 to the 3 in, get rid of the k, and now we've got a number there instead. So 1 kilometer is equal to 10 to the third meters, or 1,000 meters. Because k equals 1,000. So we're just subbing in the number for the letter. If both of the units have prefixes that we're converting between, you can use 2 steps for the conversion and have the base unit in the middle. So for example, converting centimeters to nanometers. One centimeter equals, centi is 10 to the minus 2, so 10 to the minus 2 meters. This would be our first conversion step. Our second conversion step would be from meters to nanometers. And we would have some amount of meters equals 1 nanometer. The nano prefix should be 10 to the minus 9. So 10 to the minus 9 meters. So if we had, let's say, 5 centimeters, our first conversion factor, we're converting to meters first, so 1 centimeter goes on the bottom. 10 to the minus 2 meters on top. Centimeters cancel. Our next conversion step, now we're going from meters to nanometers, so the 10 to the minus 9 meters goes on the bottom, and the 1 nanometer goes on the top. The meters part cancels. So this would give us something like 5 times 10 to the 7 nanometers. Nanometers are really small, centimeters are a little small, so it makes sense that we get a really large number, because nanometers are way smaller. Positive 7. Because we would have the 10 to the minus, if we did like just subtracting the exponents, we would have 10 to the minus 7, but it's on the bottom, so we flip it to the top and it turns into a positive. So generally for prefixes, like unless you want to remember the opposite, like for the small ones, like nanometers, 10 to the minus 9, so you could also say that there's 10 to the 9 nanometers in 1 meter. That would also work. But this way works for all of them, just subbing in whatever the number version is for centi or nano or mega or whatever our prefix is. You don't have to use these exact numbers if you, just as long as you do it correctly. But this is one surefire way of getting the job done with prefixes. All right, I want to skip that example, and we'll go straight to 2 metric prefixes. So we want to convert 5.52 times 10 to the minus 5 centiseconds to, what is this thing that looks like US? Microseconds. So that's the Greek letter mu. Mu for micro. So starting with centiseconds, what's our base unit for time going to be here? Seconds. So we can go from centiseconds to seconds. Can we go from seconds to microseconds? Sure can. What is centi equal to? Yeah, so 1 centisecond, the C prefix is 10 to the minus 2. So we're going to plug that in. 1 centisecond equals 10 to the negative 2 seconds. And then we've got a conversion between seconds and microseconds. So 1 microsecond, micro has the prefix, so it gets the 1. What is micro equal to? Yeah, 10 to the negative 6. And so we can plug that in. So 10 to the minus 6 seconds equals 1 microsecond. And then we just need to turn those into conversion factors when we plug it in. So 5.52 times 10 to the minus 5 centiseconds. 1 centisecond goes on the bottom so that they cancel. 10 to the minus 2 seconds goes on top. So 10 to the minus 2 seconds over 1 CS. So the CS cancels. We've now got seconds on top. So the 10 to the minus 6 seconds will go on the bottom. And the 1 microsecond goes on top. The seconds cancel. We're left with microseconds. And we can plug it into our calculator. 5.52 times 10 to the minus 5 times, cool, I deleted everything. Start over, 5.52 times 10 to the minus 5 times 10 to the minus 2, divide by 10 to the minus 6. You should get 0.552 microseconds. This is the sort of calculation that you might want to make sure you can do on your calculator, because putting in the 10 raised to the power, that's one place where I could imagine people making mistakes. Just if you haven't practiced it, make sure that you've done it on your calculator. So make sure you can do this on your calculator. We'll also encounter units raised to a power, or units with exponents. When we're making conversion factors for units raised to a power, raise the number and the unit to the power. So if we're doing inches squared to centimeters squared, we have two options. First, to kind of understand what our options are, we need to know what inches raised to the second power means. Who knows what that means? What's another way we could write that? What if it was x raised to the second power? What's another way we could write that? Yeah, we could write that as x times x. So we could expand it out. The squared means that we've got two x's multiplied by each other. The same thing for units, like inches and centimeters. So raised to the second power means that we've got two of them. Raised to the third power, or cubed, means that we've got three of them. And every time we apply our conversion factor, we're going to be canceling out one of these. So one of our options is figure out how many we have. We've got two. And then apply the conversion factor 2 times. So inches times inches is our starting. We've seen this conversion factor a bunch. 2.54 centimeters over 1 inch. If we apply that a single time, one of the inches gets canceled. And this is where some people will stop if you don't have your brain super engaged. You'll apply it once and you'll think, okay, we got rid of the inches and the square doesn't mean anything. And bad news for you, if this is a multiple choice question on one of my exams, whatever you get for this, doing it wrong, just applying it one time, that'll be one of the answer choices. If you apply it twice, so the second time that we apply it, 2.54 centimeters over 1 inch. This second time, now we cancel out the other inch, and we're left with the 2 centimeters that we want. So centimeters times centimeters, so we get centimeters squared. So you can either apply it individually, or a little bit of a faster way to do it is kind of what is being shown on the slides in the stuff that's already there. So you can also raise your conversion factor to whatever the power is. So 2.54 centimeters over 1 inch is the conversion factor that we'd use, and we can raise that to the second power. When we do that, we just distribute the 2 to everything that's inside parentheses, which is easier than it looks like it could be. So if we take this 2, the squared, and distribute it to the centimeters just takes the squared. The 1 times 1, still 1, so that stays. The inches gets a squared, so it's inches squared. And then the 2.54 is the only one that really requires a little bit of silicon, aka our calculator, because I'm not doing 2.54 squared unless somebody forces me to. So what this would look like, 2.54 squared, centimeters, also squared, over 1 inch squared. And so this allows us, especially if you evaluate the 2.54 squared, you plug it in your calculator, it tells you what the number is. It's this 6.45. This allows you to do applying the conversion factor 2 times, but in one step. You can also do this if it's raised to the third power. So if we're using volume, if you've got cubic inches and you're going to cubic centimeters, you would just change the 2 out for a 3. And that'll do it also in one step. So either of these ways, they're identical mathematically. Whichever one you like more, whichever one you feel like you can do consistently, do that one. We can also apply it over multiple steps. So for example, how many, question words, cubic centimeters are there in 2.11 cubic yards? We've got a couple of conversions that we're going to have to do, and so it's really convenient if we can do this all in as few steps as possible. So we're going to use that conversion factor raised to a power trick with this one. So starting with yards, cubic yards. Yards could be converted to feet. So let's convert to cubic feet. And then from feet, we can go to inches. So this would be cubic inches. And from inches, we can go to centimeters, so it'll be cubic centimeters. You might be able to see how this could be a huge pain to write out the calculation if we're writing out each conversion factor 3 times for all 3 of these steps. That's a lot of conversion factors. So our conversion factors, 3 feet over 1 yard, cubit. Feet to inches, 12 inches in 1 foot, cubit. 2.54 centimeters in 1 inch, cubit. So what this will turn into, 2.11 cubic yards. The feet and yards, the inches and feet, the centimeters and inches, those will all just have the raised to the third power. And then we'll have 3 cubed, 12 cubed, 2.54 cubed. And you can figure out what those are before you put them into your equation, or you can just put in the number raised to the third power, and your calculator should do that for you perfectly without any parentheses. So 3 to the third power, 27 cubic feet over 1 cubic yard. Get rid of all our cubic yards all in one go. Now we're in cubic feet. Our second step, we're going from cubic feet to cubic inches, so we apply our inches feet conversion. 12 raised to the third power. I don't have that one in my brain, so we'll ask the calculator for it. Okay, and the cubic feet cancel. And then for our last one, the 2.54 raised to the third power centimeters cubed over cubic inches. And the cubic inches cancel. And this will give us out cubic centimeters. Okay, so 2.11 times 3 raised to the third power times 12 raised to the third power times 2.54 raised to the third power. And we get a very large number. That number is 1613210.75. Fortunately for us, they're all exact conversion factors. So 3 sig figs at the start means we'll have 3 sig figs at the end. 1.61 times 10 to the, move the decimal over 1, 2, 3, 4, 5, 6 spots. 10 to the 6 cubic centimeters. Questions? This is a conversion fact, like units raised to a power, like this is kind of on the long end of units raised to a power that you might expect. We probably won't do a ton of this, but you will need to know how to do it occasionally. Like for heat capacity, we might need to know it. It could show up in problems. Do you want to try doing one? Does anyone affirmatively want to try one? All right, then I'll leave this for you to do. The red bars in the top right, that's just me covering up the answer. So if you go to the sheets that aren't annotated, the answer is up there so you can check your work. And come to my office hours if you're confused, or just send me a text or something. We can also use density as a conversion factor. We talked about density because we haven't talked about it in my other class. So I know we've talked about it here. Backpackers often use canisters of white gas or other types of fuel to fuel a cooking stove's burner. If one canister contains number 1.45 liters of gas and the density of the gas is, helpful information, grams per cubic centimeter, what is the mass of the fuel in kilograms? So we're looking for mass of the fuel specifically with the units of kilograms. We've got two numbers that we were given. We've got the liters and we've got the grams per cubic centimeter. Liters is just one unit, so I'm going to start with liters. We also have this grams per cubic centimeter. We want to get to kilograms. We could get to we could use the grams to get there. And we have liters, which is a unit of volume. Cubic centimeters is also a unit of volume, so we can use this as a conversion factor. We'll just have to get to cubic centimeters. Hopefully we're seeing that. Okay, so liters we can turn into milliliters, which is equal to cubic centimeters. Same number, different unit. And then once we've got cubic centimeters, we can use density to get to grams. From grams, we can get to kilograms. Do we have any questions about how we came up with any of that? The way that we use density as a conversion factor, we could also use it like in its equation form, density equals mass over volume. We could use that to do it. But if we look at the units, starting with a volume, the centimeters part is on bottom. So if we have cubic centimeters and we multiply, the cubic centimeters will cancel and grams will be left over. So we don't have to know the density equals mass over volume equation. The units can tell us what to do or guide us on what to do. So 1.45 liters of gas, it's a lot of gas. That is actually a pretty large amount of gas. I guess it's compressed. So going to milliliters, 1 milliliter equals 10 to the minus 3 liters. Liters cancel. Great. Milliliters is the same as cubic centimeters. I'm just going to replace it because I don't feel like multiplying by 1. And then we multiply by the density so that the cubic centimeters is on the bottom. So those will cancel out. Now we've got grams. We need to go from grams to kilograms. We're going to kilograms, so kilograms goes on top. Kilo equals 1,000. So that's equal to 1,000 grams, so we can put 1,000 grams on the bottom. Grams cancel. And what we're left with is a bunch of numbers and kilograms. Questions? Okay, so we're going to do 1.45 times 0.710. 1.0295 kilograms. Round it to 3 significant figures, 1.03 kilograms. If my mental math mathed correctly. All right, I don't want to do another density as conversion factor because we've got more ground to cover. We will have problems that involve equations. There's some extra stuff that comes after this that I just want to skip so that we can get on with chapter 2. So some problems will involve equations instead of or in addition to conversions. When using equations, we need what we want, what we're trying to go to, on a side by itself. This is just how to solve for something generally. On a side by itself, and that should be over to the left, and in the numerator. Not numerator, numerator, aka on top. So an equation that we'll be seeing later in the course, PV equals nRT. If we wanted to solve for T, if we wanted to get T in this equation, we need to get it by itself. So we need to move the N and the R. To the left side, divide both sides by NR, and PV over NR equals T. The reason that I have to emphasize that it's in the numerator is because sometimes people will solve an equation, but they've put the thing that we want on the bottom. It's in the denominator, and so we're solving for the inverse of the thing. We don't want to do that. That might show up in, for example, density equals mass over volume. I've seen people solve density equals mass over volume. They're like, okay, volume needs to be by itself. The fastest way to do that is to just move mass. And they will rewrite this as d over m equals v, which is not true. They just like magically move the volume to the numerator, which it's not there. So don't do that. If we wanted to switch that, we just inverse both sides. Mass over density equals volume. That would also work. If you're confused about the algebra and like rearranging and stuff, ask questions later. Okay, that's all I'm going to do for chapter 1, unless there's any questions. Cool.